Okay, so today I will be talking about a little-known subfield of AI known as automated conjecturing, which focuses on designing machines that are capable of producing statements that mathematicians might interpret as interesting conjectures. The goal is not to necessarily discover new theorems from the conjectures, but to study new relationships that might have been ignored in the past. And as with many things in AI, this goes all the way back to Turing, who in the 40s suggested that a good starting point for building intelligent machines would be for machines to do mathematics. And to do mathematics, the goal is simple: to prove and to conjecture. In this talk, as I've mentioned, we will focus on generating the conjectures, generating the new questions. And this field is known as automated conjecturing. So automated conjecturing is the process by which a computer will pose mathematical statements, typically but not always in the form of conditional inequalities based on patterns observed in data or symbolic mining. The system searches for statements of the form some hypothesis implies some conclusion, and the inputs to this problem are mathematical objects. These can be graphs, integers, matrices, whatever that represents the mathematical object that you're interested in. And the outputs are conjectured inequalities or equalities that hold across all of the instances that you know about. Okay. This can be either fully autonomous or AI assisted. There is a difference here, and we'll get to that later in the talk. But the goal is the same: to discover new mathematical truths. Sometimes we're lucky and we find new theorems. A lot of times we find new relationships derived from the conjectures of these programs. Okay. Now, I don't have time to go into the history of this, but it's long. This dates back to the 50s, as I mentioned, and goes all the way to present. These are the notable programs that I can think of. So Wang's Program 2, Linnet's AM, Epson's GT, Fajtlowicz's Graffiti, so forth and so on. We won't have time to talk about all of them because we want to talk about new things. So we'll focus on these programs here. The two at the top, I would consider being foundational. Just, we should mention them. Milot's work, I think, is super important and is relevant to the new things that are going on. And then my own program, TxGraffiti. Short for Texas Graffiti, it's just an abbreviation. Okay. So Wang's Program 2 is arguably, is the first documented attempt at automated conjecturing with the computer. Notably, Wang's Program 1 was one of the first to attempt automated theorem proving. But Program 2 focused on posing conjectures and propositional logic. And this system, as noted here, quickly generated over 14,000 statements in propositional logic. They look like this. Okay. And most of these statements were either trivial, uninteresting, but the mass of them together, Wang noted that he could not ever hope to go through the entire list, right? And this exposes what I would call the fundamental problem of automated conjecturing, in that a computer can systematically explore the space of true statements on your data set, but this can go on forever. Which of these statements is of interest? Which of them should you focus on as a human, or would get the attention of humans that are experts in whatever field that you're looking at?
That's right. You said true statements, but we don't know if they're true.
Right. True on the data set that is being used.
Oh, I see.
Yeah. So this is the problem, and the rest of the talk is about dealing with this problem, essentially. Okay, so technique 1, the Dalmatian acceptance criteria, which was introduced by Simeon Fajtlowicz along with Ermelinda Della Vigna as really the first really useful heuristic for pruning this massive set of possible conjectures being spit at you. Here's Shimeon on the left with Paul Erdős. Erdős would often visit Shimeon in Houston and work with him on these problems. And we're going to come to one at the very end. The way that this heuristic works is that a new expression is formed, typically an inequality, okay? And this must be true for all of the instances of data that you have. And it must also pass this significance test. So if you're looking at inequalities and you have a new conjecture, that new conjecture must improve on at least one of the instances that you have over all of the known conjectures that you have stored. It's a better bound on at least one instance. And if so, then it's admitted. This program primarily conjectured in graph theory and chemical graph theory, but its ideas are general, and we'll see how this works later in the talk. And notably, this was the first computer system to generate conjectures that actually led to research publications. So people worked on these conjectures. Erdős worked on these. Fan Chung notably proved this surprising conjecture in graph theory that the independence number is bounded below by the average degree. There's at least 60. I think there's likely over 100 publications that came from this starting around 88. 89 is when this happened. And these are in respectable journals, like the Journal of Graph Theory, for example. Okay, so that was technique one, have heuristics for kind of limiting what you accept into your knowledge base of conjectures. The second technique being polyhedral representations. So this is Malot's work with his graphedron. I'm not sure how to pronounce that. It's supposed to be a play on polyhedron, because the way that Malot worked with these things was to take each mathematical object and annotate it with a vector. That vector contains invariants. Oh, these are graphs, by the way, in this case. That vector contains entries that are invariants on that instance. So like the number of vertices, the diameter, the independence number, other invariants that you can compute on a graph. You can annotate each object that you have, it becomes a vector in space. And once you have this representation, you can find a convex whole of these points, where each of the facets on this convex whole can be interpreted as inequalities on that data set. Now, obviously, this is very computationally expensive if you have a large number of invariants in question, but for small examples like diameter versus the number of vertices, you can produce conjectures. Now, the conjectures of this program weren't as successful as the ones of Graffiti. Graffiti produced many publications, whereas I think there's only a handful that came from this idea. But I think it's a very important idea that we're going to make use of in a bit. Yeah.
Maybe I'm anticipating, but the thought that this immediately brings to mind is that, of course, we've taken this finite subset of graphs. And so if we look at a picture like this, one direction, like n less than one, is extremely well motivated and correct of the infinite graphs. And the bound in the other direction is extremely poorly motivated because it entirely comes from the sampling.
Right.
So was that taken into account?
Yes and no, but I think more so with the successor to this program called FOG.
Right.
So FOG is the direct successor to Graphdron, which Malot and I cannot pronounce their names, but their names are there. This small group updated this program around 2017 into a modern query interface using this system called Neo4j to query a large database of all connected graphs up to 10 vertices, so millions of graphs, right? And they would compute these approximate, in that case, approximate convex holes, but there would be more information than just the convex hole. FOG was not just about finding new conjectures, it was about finding extremal graphs. So they interpreted the vertices of this polyhedron as possible extreme instances of graphs. And if you look here, the diameter of these graphs is colored, and you can see that around this boundary right here, they're really high. And that one vertex right there has a really high diameter relative to that measure and that measure. So there's an additional part of this program where they would perform operations around these extreme values or extremal instances to see if they could break the facet that occurred right there. Because again, this is just a finite set of all possible graphs. So you want to look for those counterexamples. And indeed, even GraphDrawn had a similar type of mechanism. Another program called AGX definitely did with the thing called variable neighborhood search. And these programs together did find counterexamples to the conjecture of graffiti, oftentimes bettering them, finding the true facet that was existing there. Okay. Now to my program, TxGraffiti, short for Texas Graffiti. I wrote this starting in 2015 or so, and then had a working version in 2016, which I did in isolation. I can't emphasize this enough. I was learning to program. I was a PhD mathematics student. I did not know the literature on these prior things. It's actually pretty hard to find some of the early papers on automated conjecturing. So I just kind of went with what it meant to conjecture for myself. Later discovering that I was rediscovering things, had some new stuff, so forth and so on. But the idea was simple, it's just to combine heuristics, optimization techniques, geometry, enumeration, things like this, to find these nice linear types of bounds, sometimes nonlinear. And as the name suggests, I was inspired by the original graffiti. I was an undergrad student at the University of Houston downtown. 3 of my professors were PhD students of Fajtlowicz. They knew of his work, they would talk about it. And then one of the professors had her own conjecturing program called graffiti.pc. So I knew about these things, and it was always like a goal of mine to somehow make them. And the goal from my conversations with Fajtlowicz would be to this quote here. So one should always make the strongest conjecture for which no counterexample is known. You can argue that's not the best way to go about things. This is how I thought about things at the start. Okay, so now with what follows, I'm going to give a overly simplified version of the program. Maybe if we have time later, I can talk about some additional things that exist. So let's start with what I call a knowledge table. So you can have instances of mathematical objects, but to recompute things over and over again on these objects, especially, for example, graphs, you might be computing things that are NP hard. You don't want to do that over and over again. So I like to take a set of objects and compute a table and then just update the table with new examples as I go. That's this knowledge table. And that's what TxGraffiti works with now. So it's a pre-computed table with both Boolean and numerical properties. And it works as just a structured knowledge base for the AI to work with and to explore. Okay, so suppose we have some small subset of graphs. We take these things and then we can map them to a table like this. So like independence number here, order is number of vertices, matching number, and then some Booleans here. And I like to keep a base class of things, something that's true on all of them. So I'm not just looking at graphs, I'm looking at connected graphs. That's like the base graph. So this is tree and connected and regular there. Okay, so once I have that, I need a way of generating inequalities. Now, there's many different ways you can do this. The original graffiti program hard-coded a bunch of different examples, like you select a target to conjecture on, and then check, is that less than or equal to other one plus another one? Is that at most 2 times another one? You can hard-code all kinds of combinations, and then just check if those are true. Another way, which I did back in 2016, was just look at ratios, take the maximum of the ratio, that's a constant C, so you get target is at most C times other thing, the minimum, you get a lower bound. But with time, I stumbled across a linear programming technique that I was reminded of when I was in grad school. I'd taken linear programming optimization courses. I was like, oh, that might be useful here. And it turns out it is, but you have to iterate quite a few times. So it's the next technique. So suppose we focus on a target independence number, alpha, and we want to find a upper bound in terms of another parameter, the number of vertices, the order. So what we can do is we can solve a linear optimization problem where the feasible solutions give us inequalities. So for example, if that's the target, that's the other thing, and those are coefficients. This could be a vector. I'm doing it in 2D for visualization purposes, but it could be target versus that and that, target versus that and that, or any number of combinations, but for simplicity, just one. So any feasible solution to this program gives a bound. And this M slack constraint is forcing that this and that are tight. So for minimizing that M, we want this to be as tight to that as we want a strong inequality. And on this exact data, it would look like that, which gives a conjecture. The independence number is at most n-1 in this case. But okay, what about the other ones, right? So what about a lower bound? Well, we just flip the feasible solutions, and then we get lower bounds. Solve again, we might get something like that. So for each other, if we're just doing versus one, we could do versus two, each combination of two. Versus in the connected column here, we get an upper and lower bound. But then we can do the same thing for the trees, right? Sometimes we want to look at subsets of the entire set. So these would be all the trees. We solve the same optimization problem again, and we get, if it's connected in a tree, then we get independence is at most n-1. We do the same thing for a lower bound. We get maybe 2/3 of n is a lower bound. But also notice that I'm storing some metadata up here. This will come into play later, where the touch here is the number of times it equals. It's our first way of giving a measure to a conjectured inequality on mathematical objects. How many times does that thing equal? Because we don't want loose inequalities. We want tight, strong ones. And we also keep the set of objects where it does equal. Again, we're working with graphs, but these could be anything. Okay, so let's move to regular. Get that upper bound. Move to lower bounds, we get this. And already we've gotten 6 conjectures of alpha in terms of n over each of those different hypotheses to check. Yeah.
So the coefficient is A1, they are in R, so they are real numbers which you're going to represent using some floating point number on your computer. So how can you?
The Python fractions module.
Okay, so it's not just.
Yeah, there's a check after post processing to see if that that rounded ratio is not actually true, because that happens sometimes.
Okay, so
Yeah.
It's not just any real numbers.
Yeah, I limit them to be, well, at least for graphs and some other fields, I limit them to be nice ratios. Okay, but that was, so this, we went through the list, that versus that, that's the target versus these things there. But we need to check target versus the other one. However many other invariants exist, we should check, because we don't know what the importance is. We just let the program do it. So the process continues. For the connected graphs, that versus that, we get an upper bound of alpha is at most twice the matching number plus 1. By the way, the independence number is the cardinality, the maximum cardinality of a set of vertices that are pairwise non-adjacent. There's no edges between them. The matching number is the maximum cardinality of a set of edges that don't share an endpoint. So those are most natural things, like easiest to describe in a talk. So hopefully you understand what those are. Okay, so we do the same thing there, upper, lower, move to trees, upper, lower, and then move to regular, upper, lower. Okay, and we're up to 12. But we also can apply convex hull approximations in this small dimension. So there. So then we would get that upper bound. These do differ, by the way, between the iterated linear optimization and the convex hull approach. And we just do the same thing. For the sake of brevity, I'm not going to move to the other ones. I'm just going to do it for connected and leave those up there. And we get that fundamental problem again of like, which of these is of interest, right? you can't see anything. So this leads to, by the way, we were only dealing with alpha versus two other things and three different hypothesis choices, right? And we only use iterative optimization and convex hull. There's the ratio thing that we also can use. There's many more invariants to consider. This blows up quickly into the thousands. So again, we're still in like the old realm before we get to new things. There are post-processings that we can do. And these are the basic heuristics that I used since 2019 or so. I didn't have these names for them at the time, but these were what I was doing. So the first one is the halo heuristic, named after my youngest daughter, which essentially just says you have to get rid of duplicates. Now, each method is going to produce conjectures, right? So you can obviously get duplicates. But what's more, the way that these things are computed, especially when you have more than one invariant, they can look very different. So behind the hood, there's a symbolic algebra system that I had to write to manipulate them into a common form so that I can tell for sure that these are like the same conjectures. And then once I know that they're the same, I can identify them like, oh, that one is the same as that one. This one probably looked like alpha plus 4 greater than or equal to 2, but it was manipulated to look like that. And then that's the same as that one. That's the same as that one. So we just get rid of the duplicates here.
Can I ask a question?
Yeah.
I mean, if these are the faces of the convex hull of some polytope, aren't different faces definitely authentically different inequalities? Like, I'm confused about how you could get this.
Oh, because the linear programming and the optimization, the convex hull might find the same one sometimes.
Oh, so this is like everything that comes from all the methods you said.
Yeah, just
I
two
see.
methods, but then there's also like there's like the ratio method and
I see.
yeah. So you can get different ones, and the convex hull can produce them in a way that looks weird compared to the linear programming way.
Okay, but if you just did convex hull, then you would get.
Yeah,
the
you
eight
just be fine.
ones. Okay.
Are you finding some approximation of convex hull?
For the small dimension, I can just compute it. But for larger, we'll get to that shortly. Okay, so the Hazel heuristic just.
High order relations is just kind of change the embedding or.
So if you wanted like some maybe like quadratic terms, or yeah, so you can add column, you can data manipulate the knowledge table. You can say mu squared, add that in. And that's actually what comes in later in the talk, where the best way to do this is to kind of prompt an LLM to say, what should we add to this knowledge table? Yeah.
Can you just re-explain how you decided that things are the same?
Oh, well, these here. So they are, the strings are exactly the same. And I had to like employ some symbolic algebra to get them to all have a common form so I can tell. All right, next is the Morgan heuristic, named after my oldest daughter, which looks at only keeping the most general statements. So again, my philosophy, which is not the correct one, maybe, I don't know, was that produce the best conjecture, the strongest conjecture, most general conjecture possible. So if you look here, you'll notice that we have connected, then alpha is greater than or equal to 1, but then connected and regular, alpha is greater than or equal to 1. Now, because I'm a graph theorist, I can obviously, well, anyone, I guess, could tell like that this is a subset of that. But in practice, you just have the table. So that is actually a callable function in the program. That's a callable, there's a logic system where I can apply that to the data frame and get the names of all of the things that satisfy the hypothesis. So then I can check if the subset of the hypothesis set, if this hypothesis set is a subset of that one, strict, get rid of it. It's less general. So get rid of that one. Same thing here, connected versus connected and tree. Okay. They're connected and connected and tree. All right, so we're making progress. Okay, so next is this modified Dalmatian heuristic. So the original Dalmatian heuristic of Fajtlowicz is Graffiti with an acceptance criteria. You only let in a new conjecture if it's better on some instance than some of the set of known conjectures.
Can
And-
I
Yeah,
ask a question about the Morgan?
yeah.
If you get rid of the more specialized one. Yes. And then you kept the general, more general one. So what if specialized one is true, but the generalized one is false?
Well,
You are losing some important conjecture.
not quite, because to me, if it is important, when I add the counterexample, which there has to be a counterexample if the more general one is false, right? There's some counterexample. I add that to the knowledge table. I conjecture again. The more general one would no longer appear. Does this one still appear? Right, so it's like an iterative feedback loop where you pose conjectures. Like this is a very small data set we started with. Some of these are false. We should write down the counterexample and put it in, conjecture again. What pops out? The more general false one wouldn't appear again. Do this again, do this again. At least with graph theory, you don't need to do this that many times before you start getting like really difficult or actually like theorems. But again, this is just my choice. We don't, in fact, the Python package I have for this, you don't have to. You can say, you can pick which heuristics you want. Okay,
So if your knowledge table is not that complete, then how do you know that your knowledge table is good enough?
say that again.
I mean, you have some kind of some known result, right? You call it knowledge table.
Yeah, it's just each row is an instance and the columns are the values.
Find table to refine the conjectures.
Yes.
But the knowledge table is not complete, right?
Right. Think about how like a mathematician would conjecture, right? Like a mathematician is not going to leave out an example and formulate their conjectures, right?
My concern is you are relying on some incomplete table to refine your conjectures. So that's my concern. Is it
Well,
okay?
I understand the concern, especially since like from like a machine learning standpoint. However, I think in this case, from the point of view of a mathematician conjecturing, we use all of the knowledge that we have to trace out, we don't leave anything out. It's like trying to mimic that process that a mathematician would do. It turns out that this seems to work, especially when you have linear types of bounds. You start increasing the complexity, then you start overfitting that little table that you have. Okay. Okay, so the next up is the Dalmatian heuristic, which was an acceptance criteria for the original graffiti. However, when you're making conjectures using that acceptance criteria, early on, you could accept something that's weak, and then it never gets pruned out later. So I use it as a post-processing. I adapt it for post-processing to get rid of things. It works like this. So notice that, let's see, this conjecture here, it touches once on that instance there, G5. But G5 is strictly contained in there. The set of sharp objects of this one is a strict subset of both of those. So get rid of it. This is a way that we can get rid of transitivity in a sense. So these two are, they're sharp sets or strict subsets of these. So that heuristic says to get rid of them. Okay, now if we add more data, there might be that this one is better on a new instance, it might pop back up. Okay, same thing here. These sharp instances are strict subsets of these, so they're less strong in a sense. So get rid of those. That is a strict subset of that, so get rid of that. And finally there. So if you look, the list has like drastically shrunk. So there is one final step. Remember, there is a numerical measure associated with these, how many times it equals. We can then sort by that number. The highest touches are the strongest inequalities, they go at the top, and then the ones that are less go below it. Okay, and this was essentially my program up until maybe 2 years ago, was this procedure, which is still alive on this website here. It's a TxGraffiti Streamlit app where you can generate conjectures, and you can definitely see the way that this looks. So suppose we want to conjecture on the independence number. Let's just choose something quick like connected graphs. It does all those steps really quickly. And then you get something like that. That says I don't know what that means. I don't remember seeing this one. The independence number is at most a half of the graph energy of the line graph plus 1. What is the graph energy? It's the sum of absolute values of the eigenvalues of the adjacent matrix. So take the line graph, compute that, then you get, and you can see that it's tight. And it's at the top because the touch is the highest for that one out of the other ones. Oh, that's a weird one. You talked about nonlinearity. So there are a bunch of indices that you can compute using the degrees. I asked GPT to help me come up with brand new indices kind of derived from these. One of them is the reciprocal geometric arithmetic index for the 2 degree. GPT came up with that. That's the 2 degree, the number of vertices at distance 2 or less to the, not including itself. So just putting that into the column of the knowledge table, you get a nonlinear bound that no one's probably ever seen in their life. You can also come over here. I know there's going to be a talk on graph products. So there's 4 famous graph products: Cartesian, tensor, lexicographic, strong product. You can pick some invariant. Let's pick one, I don't know, the domination number. Let's conjecture. Shouldn't take very long. And again, these are all relatively small data sets. It's like 300, 350 objects, but they're special objects. I didn't mention this earlier, but when I started writing TxGraffiti in 2015, 2016, I didn't really know how to program. I taught myself to program because I wanted to do this. So I didn't know how to find graph databases. So the data set I made was from me combing through journals and seeing pictures. I would write the adjacency list of that picture and save it. So those examples are special, right? If they appear in a paper, they're a special counterexample. They're a part of an infinitely sharp family of graphs for some inequality, something like this. And interestingly, cubic graphs where every vertex is degree 3, were the easiest for me to draw. So I have, my small data set has quite a few of those. And some of the most interesting conjectures of this version of the program are on those types of graphs, cubic graphs. All right, so I don't know what that says, but it says something about a product in relation to a sum, product relation to a sum, Cartesian product and tensor product relation, domination number, minimum cardinality dominating set, independent domination number, maximum cardinality of a minimal dominating set. Maybe that's true, I don't know. But that app is essentially the program as it stood for the majority of its time. Over the last 2 years, though, there's been more interest in this. I've been actually meeting people, talking more about this. I was in isolation for a long time, so it stayed the same. Okay, so let's inspect these. Trivially true, trivially false, false, true, false, true for non-trivial connected graphs. And then at the top, the one I like to talk about the most is this. This was a new theorem that was discovered by the program that for any regular graph, the independence number is at most the matching number, which can be generalized to this, that minimum degree times independence number is at most maximum degree times matching number. In the background now, I would have found that because my inequalities are very specific, it's coefficients times variables plus some additive constant. I can check automatically ratios that equal 1 or whatever the coefficient is, which now we'd find this. But this is, I have to emphasize, this is surprising, right? Independence and matchings are some of the oldest concepts in graph theory. So are regular graphs. I didn't believe that that was, like, I ignored it for months because I was like, oh, that's surely false, known, whatever. And then finally, because my system kept on putting it at the top and it was annoying me, I shared it with some colleagues. They thought it was obviously false or true or like known. Turns out it wasn't. That is a surprise. But yeah. So, but on that note of surprise, I must go back and think about some of the early work of Fajtlowicz that I know he thought about, but is probably not written anywhere. But what does it mean to be surprising? So I don't want to quote Fajtlowicz exactly because I don't know, I wasn't there, but I know that he thought about this. So this is my interpretation of this. So in graph theory or other fields, you can define like atomic operations in a sense, the smallest pieces of the field. So you have a vertex. Once you have a vertex, you can define an edge. Once you can define an edge, you can define a neighbor. You can define incident edges. And then as soon as you have those, you can define independent sets, independent vertices. There's a common operation of maximization applied, and then you get these numbers. And you can create this like tree of possible invariants to get to. And then what you can do is you can look at how close the invariants are in that tree, right? So one way of saying surprising is that you have a conjecture involving an invariant to another one that's like really far away. That would probably be surprising. Some of my favorite conjecture of the program has that form. But this one kind of relies on like time, like how long have these notions been around? So if there's a lot of time that has passed and they're close on this like tree of operations, then that might be an indicator of surprise that we can work with. Again, we're trying to come up with heuristics, measures, ideas to filter the space of all statements that we want to study. Okay, I have to move quickly. So recently with I'll call it the IRIS group, there's a paper that we published at a workshop at ICML this past year, where we took a geometric approach again to somehow defining numerical values for linear conjectures. So treat each object as a point in RK, store it as rows in some data matrix X, and H is going to denote a linear conjecture. That's A times some invariance plus B. Okay. So it looks kind of like that. And then we define this touch set. We already know what a touch is. It's equal. But some fields, like if you try to conjecture on matrices, where there's real values, floating point, the best you can do is epsilon, get close to it. So define that touch set for a conjecture to be how close to zero epsilon it is. So the touch number in the previous slides is just that, but this is like normalizing it to make it consistent with the rest of the values. But when considering like strength of a conjecture, you could have like a bunch of points like this. And there's like a bunch of instances right here, which would give it a high touch value. Or like even this kind of thing, which is where my friend Jesus at UC Davis proposed this normalized rank, which we had many discussions about, in that we can take those vectors, those invariant vectors, those xi, we can stick them in a matrix and compute the rank to get a sense of how diverse those objects are. Are they essentially the same? Or do they have different invariant values all over the place? And that would be a way of saying it's not just like paths that equal, it's like paths in the Peterson graph and other things maybe. Just a way of trying to measure that. My favorite one is that. This is just from me observing the conjectures over the years. So the diameter of this set is just the length of a longest facet in the data that you have. Like if you were to like calculate that. So you look at the diameter of the touch set versus the diameter of the entire X. That gives you a value. And once we have these values, we can not only focus on conjectures, but calculate them on known theorems. So like Barnett's theorem has normalized touch of that. So these are in polyhedral theory. R is 1, L is, we get numeric values to associate with these things. For here, it's kind of funny that Jovac's theorem on the data set is so little right there. I was kind of arguing that this should have been, because I like the long range, this diameter measure. Okay, but those are just measures of conjectures on the data. But what about measures of conjectures with relation to other conjectures that you know? So I define this set D to be the set of all X in X. X is the data matrix consisting of all those invariant vectors. And then H is some conjecture with A, B. So this less than or equal to the min over all the other conjectures. Essentially, this is a way of checking Dalmatian, right? Like how many objects in there is this thing better than the other conjectures at? That's what that set is. You put an indicator variable on that, that's the Dalmatian heuristic. This is the rational version of that. Count how many it's better at other conjectures than, and divide by the total number of instances. And then the proximity. But I want to move, well, what I can say is that we have measures for a conjecture with respect to data and a set of conjectures, measures for a conjecture with respect to data. And with those two things, we can, in a sense, like generalize graffiti, right? So produce inequalities by manually checking some things on a target alpha. If that Dalmatian value, indicator variable greater than 1, except conjecture, sort by that touch, it's essentially the same. But you can come up with all kinds of different combinations of acceptance, sorting, filtering using this. Which in practice, like this is one way that we used in the paper. You can see a bunch of facets are popping up and then some are getting removed because they don't satisfy one of the numeric values that we wanted. And then over time it settles. And then each of these would be conjectures on the random data set here. Okay. So these types of techniques become expensive when you have a lot of rows, a lot of instances. So for example, this Calabi-Yau threefold data set contains 7,890 instances. I didn't let my program run the entire time to try to conjecture on it, but it was taking too long. So there is an older technique that I used to use when my computer was way slower, and I would just conjecture on like the top set of things, and then I would check the next row instance. Was it a counterexample to any of the conjectures that it made? If it was, add it, and then conjecture again. That way you don't add every 7,890 of these instances. You just add some collection of them. And so here, I have a link, WOW3, written on the wall 3 of graph theory, number theory, string theory, conjectures. I think that one I was showing is quite a few. A colleague of Mike found counterexamples to several of them, but that's to be expected. You want to find counterexamples and then add that to the data. So we see that this sum of Hodge numbers is greater than or equal to some coefficient, something squared, it's nonlinear. But how did I come across that? Well, so many fields of study require the creation of interesting columns, as I mentioned. And then one may prompt an LLM to do this for you. Find the new types of columns to put in that would be interesting. I asked it what Mike would find interesting, and this is what it helped me do. It said, add these relevant. So apparently, Mike, to the LLM, you would like these things. The sum of Hodge numbers, the difference, the product of Hodge numbers, a ratio of them, some chi density, so chi divided by the config sum, these types of things. And you get, I only put a few up on the website, but I have hundreds of conjectures on these Hodge numbers and chi densities and chi, and I don't understand what they are, but I use an LLM to help me fill in the data to produce them. Of the ones on the website though, I think there's something here for this top one. That's why I included it here. Okay. Okay, so with the Iris group that I'm working with, this is a well-known idea that you can search for counterexamples using reinforcement learning. For conjectures, or say the form that and most that, what do you want to do? You want an agent to minimize that and maximize that with the hopes of breaking the conjecture. This is how a human would do it. And in our experiments, I don't have the exact model design up here, but we have started to find counterexamples which get automatically put back into what I call this optimist-pessimist framework. This is my goal, my long-term goal. I hope I can reach this, that the optimist agent is essentially like TxGraffiti or something that applies these conjecturing techniques, provides a list of conjectures to an agent, an RL agent, that can search for counterexamples, update the knowledge table, and then this automatically happens again. I have a preprint on the archive called The Optimist, where there's a notebook where you can do this interactively. It doesn't have RL, but you can pretend to be the RL, and you can see it learn in real time. Which leads me to something that I thought about when doing this RL stuff, which is this notion of Ramsey numbers, which R is the smallest integer n, so that every blue and red two coloring of the edges omits either red, KR, or R. These are known for R is equal to 3. There are bounds for 5 and 6. And Erdős thinks that we would never do R66, but we could probably do R55 if we really put our minds to it. So I wanted to conjecture bounds on these things. Can I improve those? So I came up with the following game. The board state is Kn embedded in the plane in a circulant geometric way, where there's actually meaningful distances. And at each play, a player can color a single edge. It can choose a circulant coloring, which is a distance coloring. Or it can try to finish the game by calling a SAT solver. So the player gets to say, well, actually, let's look at it. Let's open this link. Oh, here's the game. But let's make it kind of interesting. It's 17:4. Let's enable these things. New game. All right, so let's do a circling coloring to start. Maybe distance class 7. No, 6. I've gotten pretty good at this. Okay, let's let the agent move. It did it, circling coloring. Maybe I'll just play a single edge to be safe. So 0, 1 should be blue here in a second. Let the agent move. Oh, it didn't play. So I'm red, it's blue. Maybe I'll attempt a SAT solve. But okay, so that's the game. You can do these things. Well, what I like to do is if you ever reach a tie, if you force a tie, you win automatically. A tie is a good coloring. If you tie, you don't have a monochromatic KR, your opponent doesn't either. So that's the game. We have this geometric embedding. We can use a simple GNN, which I looked up, there was a mu0 GitHub account. I went and it's outdated now. I had to like update it to add a GNN. Basically writing it from scratch. And it looks like this. Let me just play. I'm using my MacBook Air GPU. Let's look at maybe 5. The lower bound is 43, so let's see if we can go to 45. Start at 8. Make this small for demonstrations. How many SAT calls? I'm gonna make it super big. By the way, you have to penalize it for making SAT calls that take too long. So I have a time limit and it gets a negative reward if it calls SAT too early. Okay, so you can see we started here at R55. It found a witness, a tie. Now new bound is 9. It's advancing, says new bound is 10. We don't have time to go through all of that, but it works. It's able to get up. The highest I've gone, I'm with my laptop, I've gone up to 39 with R is equal to 5 and N is equal to 39. It seems to get sucked. In fact, I conjecture that there is no way to circulate color iteratively. K39 to get no monochromatic K. There's a still playing. All right, I have a few minutes I'd like to mention. The last thing is there are people interested in number theory here. So this Fajtlowicz Erdős graph is the graph obtained from taking a vertex set 2 to n, where 2 distinct vertices, u and v, are adjacent if and only if their GCD is not equal to 1. This is what an example looks like. And if you notice, this maximum independent set of vertices is a set of prime numbers. In fact, the prime number function pi of n is equal to the independence number of this thing. So let's maybe introduce some graph theory here. There's a well-known computable bound on the independence number called the residue. So you take the degree sequence, you put it in non-increasing order, like that's the degree sequence, each vertex degree. Delete the largest term, subtract 1 from the following 2 terms. You get, oh no, did I do that right? Delete 3, 2, 2, 2. So that, yeah, that should be 1, 1, 1. Talk to me after if you want to know how to do it. It's a very simple algorithm. And what I noticed was that when I conjectured on the independence number and the residues, and I was computing that as well on these graphs, I noticed that for 1 to 14, pi equaled r. This computable degree sequence elimination thing. But then I got rid of those and I conjectured again. From 14 to 25, non-inclusive 14, pi was equal to r plus 1. Okay, is this pattern? I got rid of those, I conjectured again. I saw that pi was equal to r plus 2, contiguous interval. Got rid of those. Pi is equal to r plus 3, contiguous interval. Get rid of those. Pi is equal to r plus 4. Pi is equal to r plus 5. Or pi is equal to r plus 6. I didn't check in this old picture, but this essentially continues most of the time, with the exception of like very specific weird cases where it's not exactly monotonic in the same way. Like sometimes the residue goes down by 1, but then it hops back up and starts catching back up. Which, when I brought to the attention of Jeff Ligarius, and he spoke with Fan Chung about this, he started looking at this. I'm not a number theorist, and noticed that he asked me to look at the ratios of these things. So this is the ratio. So this is pi over r. And this is up to 10,000. I eventually checked up to like 100,000 or more. And you can see that this residue is tracking well with pi of n. So we claim that there exists a C naught in this interval such that these are basically the same, which Jeff Ligarius was able to track down some super old papers that I had never seen. And this originally came from Fajtlowicz with the original Graffiti and Erdős playing with Graffiti, conjecturing on the, so it's old. And indeed, it's something like this, pi squared over 6 minus 1, which was, I understand now, but at the time, I was like, what is that? But there is this, I wanted to look further, so I conjectured on a generalization of the residue called the 2 residue. I can define what that is later, but looking at the 2 residue, I see that the 2 residue is always strictly greater than pi over n, and there is some other interesting constant here. And I went up to 10,000 on this one as well. And I did it for the 3 residue, It's a smaller band. There's a very interesting pattern here that was discovered from my iteratively conjecturing against pi of n in terms of all of my invariants and residue always being at the top. So again, if you are a Python programmer, please go to my TxGraffiti, it says 2 repo. I've tried my best to write good docs for this. There are unit tests to make sure that everything works right. There's installation guides. You can recreate older programs using the modular interface that I have for this. There's the WoW3, the app. And then finally, I think that all of us as AI for mathematics researchers should find this book. This was my favorite book, but then I gave it to Terrence Tao at MathFest, somewhat regrettingly now, because it's very difficult to find. This is from 2001, a workshop on graphs and discovery, where the majority of papers in here are about AI applied to discovery. And it seems, it almost mirrors the kind of ideas that we all have been talking to. I'm conjecturing, some rather like approximating, there's constructing. I think that everyone should know about that. And that's it. Thank you.
So we have time for maybe 1 or 2 questions, please.
When you try to set up to an automatic CR improver, so you CR improver from from the beginning, but like from nothing and try to put the conjecture, but you could use it as well to prove conjectures.
Mike, do you want to say?
That's the current project.
Yeah, I do have, so that TxGraffiti package, there's like one bug left, but there is an automatic way to produce lean statements, lean force statements, with the specific goal of creating a benchmark list to provide to an automatic theorem prover, which hopefully the goal is there's the counterexample pessimist agent that tries to let that run for a little bit. And then once the conjectures stop being disproven, then those are the ones you send to the theorem prover and see, there's a lot to be, I'm excited to see what happens in the coming years with this idea. Yeah.
Right, equality instead of inequality.
Yes, it automatically detects equalities.
Yeah.
And when equalities are found, it saves them. It doesn't do the heuristics. It's it's very rare that happens. In fact, I'm not going to mention the journal's name, but I'm currently about to submit revisions on proving only one equality at a top graph theory journal. It's been accepted with revisions, but I'm not saying, I don't know what they're going to say about the revisions. They were very happy with it. They were very surprised by the conjecture.
So you can put in lean in this loop somehow, right? Just eliminate those conjectures which are kind of trivial or easy to prove. But we also works with I guess more recently LLM-based check, right? So kind of whether this conjecture is is relevant or important.
Yes, I think that there's something to be said there, especially since if you don't know the field you're doing it with, then that would be very helpful. And at RelationalAI right now, my intern is doing exactly this. So we're using the same system to conjecture on non-mathematical scientific data. So conjecturing on, I don't know, MBA data or whatever that would be useful in an industry setting. And then those conjectures are propagated up the same exact way, but then we tie into various APIs to get translations of them in importance to then give to the user. Yeah.
I mentioned you're working on apps for these conjectures to formal languages. So I was kind of wondering, what do you realize this thing that's using or this is model-based?
So I'm only translating them to lean. Now we have help writing these into MathLib.
These are pretty easy because they're, these linear affine relations on predefined invariants. And so we just cut it up all the invariants and then it's easy.
Like when you're exporting the conjectures to the formal language, you're doing it manually or?
Well, that's the translation is automatic because conjectures have such a simple form. We write out, we define the invariance manually.
Yeah, so
And then the conjectures themselves all have a very simple form in terms of the
yeah,
invariance.
remember how I mentioned that I have like a symbolic manipulation, algebraic manipulation to get them into a certain form? Once they're in that form, it's easy to put them into lean once you know the exact lean form that they should be, which I didn't know originally and haven't done it yet, but it's basically there.
No, it's really, it's very simple because these are such simple conjectures.
Yeah. I would think that the majority of what I was talking about today is all classic AI. Less so modern techniques, with the exception of well, mu0 is like old now, but yeah, for the most of it, it is heuristics, data mining. It's automated conjecturing. It's like its own thing in a sense, but a classic AI type of thing.
Another question. So it's a suggestion of another use of LLMs. So at the beginning, you say that when you get started, you looked at a lot of papers on graph theory and you just get,
Yes.
finding new interesting graph. Have you looked into something like using, I don't know, deep research or something like that? Because if you don't know about Calabi-Yamaha, you could say, okay, deep research, find me the most interesting or a whole lot of interesting Calabi-Yamaha.
Yes, I have done that with number theory things. For example, it seemed to be very interested in conjecturing on the number of steps to reach the collapse termination time. That was like one of its favorite. I wouldn't have thought of that. And there are some other properties of integers that it looked at. Yeah, it's pretty fun actually, because you don't know what's going to pop out, and if you have a vague idea of the field, you can see, oh, wow, this I had no idea. Where did that come from? And it can conjecture in like any field if you just are able to tabularize it.
I have my favorite data set of some subject like with a node invariance, and
Mhm.
can I kind of adapt and just?
Yeah. Yeah, there was a well-known Nature paper on that knot invariant.
Yeah, I mean, I'm just saying this was one.
Yeah,
That's the first, one of the, very influential papers is like, collaboration with DeepMind of.
yeah, I remember when that came out.
Inequality with
Yeah.
most variants. It's like,
Yeah, when it came out, I was like, what? And I went like, yes, you can conjecture on that easily.
so.
You have to do the truncating thing that I did for the string theory stuff, like steps, and only admit counterexamples, but you can do it. It's
So one question I in your numerical rating of conjectures, which I find a very interesting point, but do you penalize? I mean, I would think that if you sort of took a arbitrary inequality that came from your long list of inequalities where I have some large set of graph invariants, let's say that I study, I would think that a typical one would be not very sparse. Like it would be sort of some linear inequality involving 15 different invariants of the graph or something like that. So do you punish those? Do you consider those sort of inherently less interesting? I just feel like the examples you gave are only very few.
So in graph theory, from the start, so this is a funny story. When I started writing this, I was doing that where it had multiple different graph invariants, the sum divided by others. I sent that to my good friend Yuri Caro, and he was disgusted. So I learned early on, my graph theory colleagues, if I sent them anything that wasn't simple, one, maybe two invariants, they didn't want it. So I put into the old system a check for that to only limit that. Now, when I started working with the Iris team, which is focusing on polyhedral data, face counts, things like this, they wanted every single one. So I just adapted it to allow that, where you could have 100, and then inside that 100, we would notice series appearing. Like you could collapse this into like a series with an index like I and K. So it just depends on the field. And you can actually this is how you conjecture on things with the thing. You can say you can limit the I forget the keyword, but it's you can say 3. That's like the max num. Like you can limit it in there, and depending on the field, you can choose which ones you want.
So you're saying sort of what makes an interesting conjecture is in some sense a sociological question, not just a mathematical question.
Yeah, deep research should answer that.
Played with graph spectra.
Yeah, so graph energy is like one of them, but there's also some other ones that have the ability to do this with. I can't think of any conjectures off the top of my head. We saw one earlier I'd never noticed before. It's like the independence number and the energy of the line graphs for some reason. Yeah, it's an exciting field, and I hope that I can get more help in doing this since I've been doing it by myself for so long.
Thank, all right.